Хорошо. Значит, я начну тогда опять по-русски, а потом, видимо, переключусь на английский. У меня вот этот мегаплан с минимумом доказательств поговорить про представление алгебры. Ну, можно, конечно, еще про группы поговорить, но это примерно то же самое. Во-первых, чтобы вам не было так страшно, пример такой, совсем пример, в котором слова алгебры ли нету. Вот. Очень должен быть понятный пример. Пускай у нас есть многочисленной степени n от двух переменных. Размерность какого пространства? Что? Ровно. Да. Пространство размерности n плюс 1 на... Так. На нем можно рассмотреть три дифференциальных оператора первого порядка.
Двух перемен.
Да, ровно две переменных.
Почему?
И давайте я напишу. Базис такой, знаете, у нас будет x в n, x в n минус 1, y, x, y, n минус 1, y, n. По x степени n до нуля.
Однородный.
Однородный. Да, извините. Вот, хорошо. Три оператора. С чего начать? Давайте начнем с этого. Смотрите, x, d, dx. Все x. Минус y, d по dy. Потом пускай будет x, d по dy. И еще y. Понятно, да, что написано? Это запятая. Просто три таких оператора. Ну вот куда первый переводит x? Давайте мы на первый посмотрим. Куда перейдет x в n?
Должны получиться по возможность. N, X.
Да. А вот это вот второй базисный вектор x в n минус 1, y, куда перейдет?
N минус 1, X в N, Y. Минус Y, X минус 1.
Еще раз, как бы ответ какой?
N минус 1, X в N, Y.
Нет. Со степенями не все в порядке.
N минус 1. А, да, N минус 1, X в N минус 1, Y. А, то же самое. Нет. Короче, на N сюда нужно.
Нет.
Почему? N минус 1, X, N минус 1, Y.
Второй по-английски.
А, и минус.
Okay, so
N минус
my plan for today is briefly to discuss Lie algebra representations. So the very first example, these are homogeneous polynomials in x and y of degree n, and we have three differential operators. I'm just asking how all the operators act in the basis. Okay, and so on. For the last one, where does y power n go?
minus n.
Wonderful.
Они так каждый раз на 2 будут, да, уменьшаться. То есть всегда там даже 0, если ничего.
Okay. Now this was the action of the first operator. Now how does the second operator act?
Центр 0. X and
So this operator moves them in this direction. Each basis vector goes
ну, на чем-то умножают,
with some coefficient. This operator moves in one direction, and this operator will move in the other direction. It will go to n x n. Представление алгебры Ли за одну лекцию. Извините, что, скорее всего, придется затянуть. Представление алгебры Ли за одну лекцию. Извините, если лекция затянется. Я как бы постараюсь уложиться, но что-то шансов мало. Okay. So, this was the action of my 3 operators on the basis. And now my claim is that if I commute 2 operators, then I get something adequate. Да. I don't want to say the answer right now, but we've done this at the first or at the second lecture, I suppose.
Компьютер, в смысле, коммутатор.
What if I take the differential operator of the commutator of the first and the second one? So magically it will be the differential operator of the first order.
Единица первого P. Сейчас. Это что значит?
Сейчас там не будет D2.
Там будет только D почему-то.
Да. Да. So, I will apply it to some polynomial P. Suppose that P is a polynomial in x and y. Okay? And polynomial, we may assume it from Vn, but it doesn't matter. It doesn't matter at all. So, it will contain 4 terms. Just we apply this to this applied to P, minus this applied to this applied to P. plus x d dy. Y d dy. Okay. Now what next? First of all, since this is constant with respect to d dy, we can move it here. Or just you differentiate the product where x gives 0. And in the same way, x can go out here. And then we need to work a little bit. What if we differentiated this by x? It will be 1 times this stuff plus x times the dx of this stuff. So it will be equal to x square dx dy plus x dy d. This was the first term. Now minus x y d square dy square. Now minus x square dx of our p.
Почему первый такой получился?
This one.
Второй слушай, x квадрат.
Еще раз, вот мы будем.
Да. Это мы вот продифференцировали x, домножили на это. Это второе с квадратное. А тут как бы просто x оставили.
Да.
И продифференцировали вот это. По x же еще должны, нет?
Что я написала?
Сейчас x.
Вот я по x написала. Y был, но хотя не написала.
Да.
А это по x.
Да, хорошо.
Я вам говорю. Okay. This one, then this one, then this one, and it will vanish. And now the last one will give us two terms. It gives us two terms, x d dy plus xy d square dy square pxy. We're almost done. This vanishes with this, and this vanishes with this. And the answer is twice x dy. So do you remember we've had matrices? We've had matrices.
Что такое матрица?
Ну, это не матрица, это не матрица.
Да.
Числитель не будет, что? Сейчас я напишу. Okay. If we say that it will be matrix 1, 0, 0, minus 1, this will be matrix 1, 0, 0. And this will be 0, 0, 1, 0. This is the Lie algebra SL2. So we have the commutator in this algebra. And we can say let this matrix act like this operator, then the second one matrix, it will act like this operator, and the third one will act like this matrix will act like this operator. Yes, I didn't check that the commutator of this one and this one gives this one, but it is very similar.
У нас получалось, что вот коммутатор этих двух это 2 на вторую матрицу. А, это как раз оно.
Ну, я единственное не посчитала пока вот. I didn't calculate the commutator of this operator and this operator. If you want, we can do this.
Он будет считать.
Of these two differential operators.
Этих двух матриц.
А это что оператор? То есть дифференциальный оператор вы также все
Это типа пока мы не понимаем, что это одно и то же.
Я понимаю. Если вы не верите, давайте считать, если верите.
Мы верим.
Okay, then if you want, you can perform this check at the seminar. That if we commute these two differential operators, we get this one. Okay. So, check out what will be the commutator of x dy, y dx. Okay. This was our very important example. So what are the eigenvalues of this matrix? No. I mean, we have a representation of SL2 of dimension n plus 1. Okay? And so this is our maximal abelian subalgebra. It is generated by one element, and its eigenvalues in this representation is n minus 2, etc., minus n. This is related to the decomposition we had last time. So, we have constructed right now a representation of SL2 of dimension n plus 1. It can be starting from 1. Of dimension 1, it will be 0. And then of dimension 2, this will be already interesting. Okay, then I add a page and write what is formally. Let us give a definition of a representation of the algebra. So if L is a Lie algebra, then a representation recall that by definition L is a vector space with some operation called commutator. It is not necessarily given by some matrices. It could be described in other terms. Representation of L is a homomorphism of the algebras from L to some matrices acting on a vector space V. So it means that for any two elements x, y from L, I can write row here. If we take matrices row X and row Y and we commute them, this is the matrix commutator, and this is just the row applied to the algebra commutator. So in fact, this is what I have checked at the previous blackboard. I said that I have two linear operators, and if I commute them, they behave in the same way as the elements of SL2. Okay.
Сейчас, то есть вот x или где-то вот эти два оператора. Ну, в смысле, вот на прошлом примере вот у нас будет два оператора. Прокоммутировали, получили удвоенный как бы оператор. А если мы... Сейчас, кто тут? Представление, то те как раз таки матрицы. И если мы их прокоммутируем, то получится как раз таки двойная матрица. Это мы проверили на первой лекции.
So in fact, if you want, I can give you the matrices in the matrix way. The previous example will be something like first one goes to n to the diagonal matrix n minus 2, etc. minus n for the first element of SL2. Then something like 0, 1, no, not 1, some elements above the diagonal and some elements below the diagonal. These operators which shift basis vectors to the left and to the right. If formally we write a row from the previous blackboard in the matrix form, it will be something like this. Okay. Okay, I think I will try to prove that that these are the only representations of the Lie algebra SL2. The only finite dimensional representations. So theorem. These are the only finite dimensional okay?
Если тут у нас как раз след нулевой, да?
Да, нет, не матрица, но плюс нет.
А кто у нас? Кстати, сейчас.
Да.
А кто у нас как бы элементы? Это вот эти вектора, да? Через касательные. И что?
Я сегодня группу не писала.
Кто тут L, а кто матрицы?
So L.
Кого мы туда отправляем?
These are L. This is row of H, row E, and row F, where H is the element on the cartons of algebra. E is this one, and F is this one. This notation does not agree with the Humphreys, but it agrees with many other books.
Excuse me, what are the stars? Star signs. What do they mean?
These are some numbers. If we We can compute them, but
It's upper triangular.
only one diagonal and all the rest is 0. All the rest is 0.
Okay.
And here all the rest is 0. I mean, if you want, we can precise it. What if we take x dy applied to applied to x and minus 1y? It will be exactly xn. If we apply this to xn minus kyk, you obtain k x n minus k plus 1 y k minus 1. So these numbers will be, for one matrix it will be 1, 2, etc. n minus 1, and for the other matrix it will be in the other direction. This 1, 2, and minus 1. Sometimes people renormalize them, and so the numbers will change, but the form of the matrix will remain the same.
Three-dimensional representation means that the GL of V is finite dimensional.
Yes, that V is finite dimensional. Yes. So sometimes people introduce infinite dimensional representations. So they don't speak about matrices, but they speak about linear operators.
Oh, so a V in this example is the n plus 1 vector space of these operators.
Of polynomials,
Of
homogeneous polynomials of the group vector n. So, what do I assume? I assume that we know that all the representations of semi-simple algebras are completely reducible. So this is what I assume. I'm not going to discuss it. It is more to the course of Lie algebras. So from here I want to study an irreducible representation of SL2. Your condition is irreducible. I will make it irreducible. Irreducible. And all the other representations of SL2 will be the direct sum of irreducible ones. This follows from semi-simplicity. Okay. How can we prove it? First of all, we take our element H. So, its action on our vector space can be diagonalized. Also, I will not prove this because such elements are called semi-simple, and their action will be diagonalizable in any representation. So, if we take V, take representation V, it can be diagonalized in some basis of V. Okay? It can be diagonalized. So it means that V is the direct sum v lambda 1 plus etc. v lambda n. On each v lambda I, h acts by multiplication by lambda I. Okay? This is one operator. Its action will not contain Johnson blocks. It will be diagonalizable. What next? Now we recall we have in the definition of the algebra we have such an identity x y. This rule. We have that it equals 0. So if we use this, we can show that no, we don't need this. I'm sorry. I love this. I just want to take some vector v lambda I from v lambda I and ask what if we apply e to it? Where does e v lambda I belong? So my claim is that it is also an eigenvector for h with the eigenvalue lambda I plus 2. I just use another one. What if we write 2e? E is our operator applied to v lambda I. It is yes, I use the definition of the representation, and I use that we know this commutator. This commutator is exactly 2e. And now it will be h applied to ev lambda I minus e h applied to v lambda I, but this equals lambda I v lambda I, and lambda I can go out. Okay, so if we move this to the left hand side, we obtain that lambda I plus 2 e v lambda I is h applied to e v lambda I. So it means that e v lambda I belongs to the eigenspace labeled by lambda I plus 2. Okay? So e v lambda I belongs to v lambda I plus 2. This is very similar to what we had at the previous blackboard. So E maps, for example, this vector, the eigenvalue was n minus 2 and it became n. This follows just from the definition of the relations in the Lie algebra SL2. Okay? So I think you believe me if I say that f, this operator f, applied to V lambda I will go to lambda I minus 2. Okay. Do you believe? Okay, then what is how can we prove that the polynomials, these were the only representations as of 2? We can, for example, take maximum lambda which appears in the decomposition. We have this decomposition with lambda n. Okay. What now? We take V0 from this V lambda. We can say that E applied to V0, it will belong to V lambda plus 2. But I have chosen the maximum possible lambda. So it will be equal to 0. It is very similar that if I differentiate x power n along y, I get 0. Okay. Now, suppose that we let us take define V1 will be the f applied to V0. So it will belong to V lambda minus 2. Take V2, I will renormalize them to agree with the literature, but it is not necessary. It will belong to V lambda minus 4, and so on. So can it happen if our representation is finite dimensional? It cannot happen. So since these vectors belong to different eigenspaces, they are all linearly independent. And so at some step of V, for example, Vm be such that Vm is non-zero and Vm plus 1 will be 0. Ну, это все векторы в нашем представлении. Они линейно независимы. Ну, это вот, на алгебре проверяют, что собственные векторы разных собственных значений линейно независимы. В смысле, они же все сидят в V. Так мы классифицируем конечные меры.
Мы сразу говорим, что это конечная мера, мы говорим, что есть конечная мера, это единственное.
Да. Конечно, мерные, мы все перечислены. Не то, что единственное. Мы все перечислены.
Там любое можно взять.
Ну, конечно. Да.
Это сразу серия представлений, просто только такого типа.
Okay. Now I will omit some calculation, but this will be really the direct check. What can we say that these are some coefficients? Now we will have that E Vi, it will be exactly lambda minus I plus 1 v I minus 1. This can be checked using our commutator relation. And if this is true, know that it will work even for Vm plus 1 equal to 0. We will write that Vm will be something like lambda minus m Vm plus 1. But we know that this one is not 0 and this one is 0.
Так, следующий и должен.
Сейчас, я хотела наоборот. Once more. Я не тут написала, сейчас. Okay. I want to relate Vm and Vm plus 1. This will be I equal n plus 1. I equals n plus 1. Vm plus 1. It will be equal to this one. Yes, if lambda is not equal to m, then Vm equals 0. Just because we apply some operator to the 0 vector. So this gives us the contradiction, and so lambda should be equal to m. So in this case, we showed that from finite dimensions, we conclude that lambda, which is the maximum possible eigenvalue, it is an integer. It is an integer, and what is our set of eigenvalues? It equals lambda, the eigenvalue of V0. So h V0 equals lambda V0 by the very first assumption. H V1 is lambda minus 2 V1, etc. And the last non-zero vector is Vm. H Vm, it will be equal to lambda minus 2 m Vm, which is minus lambda Vm. So there is one more check which I didn't do here, that indeed these m plus 1 vectors, they give us a subrepresentation. But it is... Yes, if I started with my V0, I have constructed V1, V2, etc. up to Vm. So the subspace generated by these m plus 1 vectors, this is a subrepresentation. So if you believe this, just some check with these two, with these three operators and with the relation among them, and you obtain that indeed it is a representation, and the matrices in fact coincide with these ones, with n equal to n. So this is in fact a subrepresentation which coincides with the representation from the example. But we know that all the representations are semi-simple and that we started with an irreducible representation. So in fact this subspace is the whole representation which we classified. And so we obtain that our V is in fact generated by V0, etc., Vm as a basis. And it has dimension m plus 1, and we are done. So we know all the irreducible representations of SL2. Up to some check, which is very straightforward. Okay. Any questions?
On the last lecture, we see that the set of eigenvalues is some root system. Yes?
Давайте сейчас не путать. Сейчас давайте распутаемся.
Давайте.
Okay. What do we have? We have, first of all, we have SL2. It is a three-dimensional Lie algebra. Okay. We have any other Lie algebra. We can call it G. Any Lie algebra, and it corresponds to some root system phi. Okay, any semicircle. What representations do we always have? For any Lie algebra, in fact, it has its adjoint representation. G, so representation. G such that x from G x by this one. So any Lie algebra has a representation of dimension equal to the dimension of this Lie algebra. But this is not the only representation. A Lie algebra can have many representations. So our plan for today is to classify them. So for SL2, in fact, we have what is interesting. SL2 of dimension. For example, we can construct the representation of SL2 of dimension 2. Just we multiply a matrix by a vector. Just any matrix A, B, C minus A applied to V1, V2 will be A V1 plus B V2 C V1 minus A V2. And it will coincide to the polynomials of, it will almost coincide with the polynomials of degree 1. Okay, we have two polynomials of degree 1. And what is the bijection? So 0, 1, 0, 0, it will map 0, 1 to 1, 0. So if we identify this with y and this with x, it will be the bijection. So the two-dimensional representation of SL2 is isomorphic to polynomials of degree 1. The three-dimensional one will be the joint representation. And we can identify it with polynomials of degree 2. And high-dimensional ones, so this description is using polynomials of degree m. So there are many possible representations of SL2, but we know them all. And my aim for today is to describe in some sense all the representations of n in the algebra G using root systems, alpha chains, and so on. All the stuff that we have learned right now about root systems. So, what is an SL2 triple? Do you know that let alpha belong to phi? Do you remember that in fact it was the dual space to the Cartan subalgebra? So there is some H in G, a maximal abelian subalgebra consisting of diagonalizable elements. What does it mean on the example? Suppose that the example will be here. Suppose that we have SL3. What is SL3? These are 3 by 3 matrices with trace 0.
It is maximal by dimension or by inclusion?
Both. Both. It is some check from the Lie algebra course. This is very strong condition that it is abelian. So the commutator restricted to this subalgebra vanishes. So phi for SL2 is just this one. This is phi. And we have said that H is the matrices which have non-zero elements only on the diagonal. So here, if you add any other element, if you have a matrix identity from here, it will not commute with some diagonal element. So it is not maximal by the inclusion. And how do people show that it is maximal by dimension? Every two subalgebras with this property, they are conjugate. And if you find any conjugate which contains this one, then it will not be possible. Okay. And we know that for the root system, every root corresponds to one-dimensional subspace in our Lie algebra. We have 6 roots and we have 6 possibilities to add some elements to this matrix. So for each alpha from our root system, we can find a vector from our algebra. X alpha is an element of our Lie algebra. Even it is in G alpha. If you remember the decomposition with respect to H action. And in any root system, we have minus alpha. And so we have some element x minus alpha. Which belongs to G minus alpha. And so it is not obvious, but it can be checked that x alpha, x minus alpha. So its corresponding root is 0. So it is some h alpha, which belongs to our diagonal subalgebra to H. So we have 3 vectors such that altogether they form a copy of SL2. Of SL2. So on this picture we can draw this stuff. This is the small copy of SL2. What next? Suppose that we take any representation of our Lie algebra G. So suppose that V is a representation of G. So each element from G goes to some matrix. We can restrict it to this SL2 triple. V can be viewed as SL2 representation. So we have done the very similar check such that if we apply x alpha to some element, we add alpha to the weight. And if we apply x minus alpha, we subtract alpha. So suppose that we have started, this is some, this is our, we take some V alpha from this representation of our big Lie algebra. Okay, so we have the big Lie algebra, G. We know that the action of H can be diagonalized in this representation. And we take some eigenvector V lambda. If we apply x lambda, x alpha, we get V, this one. If we apply x minus alpha, we obtain V lambda minus alpha. So in fact, inside this representation, we construct some representation of this SL2. It cannot be infinite dimensional. Сейчас просто много перескоков. Сейчас, давайте. Сейчас я подумаю, как сказать.
Короче, любое представление трехмерное SL2 содержит все копии представления SL2.
Представление SL3 содержит в себе копию представления SL2. Any other questions? Кто хочет понять, я не понял.
Я хочу понять, можно ли понять.
Ну, тут такой перескок, который вам еще в прошлый раз не понравился. Сейчас я по-русски скажу. Вы сказали, что вот у такой квадрат все представления диагонализуемы. При этом собственное значение, это на самом деле там были линейные функции. Вот. Еще раз. Мы для начала возьмем палец, в котором это все диагонализуется. Будет спойлер, вот, например, пускай для там SL3 получаем какую-то вот такую картиночку. Попробуй шестиугольник нарисовать такой правильный, ну, в трехмерной сеточке. Пускай наше множество весов, так 2, вот здесь вот 2 надо нарисовать. Сейчас как это будет? Вот так вот, вот так вот. Здесь 1, и здесь еще 2 сейчас. Раз. Вот туда. Вот сюда. Вот здесь 3. 1, 2. Все. Группа Вега. Относительная группа Вега, все симметрично. Я специально нарисовала криво, чтобы вы не думали, что все прям ровно убирается. Okay, so suppose that we have some representation of SL3, and it is diagonalizable in some basis. So the set of weights can be, for example, this set of points. These are, in some sense, elements of the dual space. So these are weights of our representation. Those lambda which appear in the decomposition. This is the set of weights, and I say that, for example, if I take V lambda from here, and I have this SL2 triple. But this SL2 triple, it will vanish, and this will be a representation of this copy of SL2. So I know that all this stuff is an SL3 representation. In particular, it contains this copy of SL2, and the representation of SL2 will be generated by these vectors. I take one vector from this eigenspace, its image, then it's in this image, and the next ones will vanish. So then I can take this one, and this will be another copy of SL, another representation of SL2. So this SL3 decomposition, viewed as an SL2 decomposition, will be a direct sum of some irreducibles. One irreducible of dimension 2, two irreducibles of dimension 3, and one irreducible of dimension 4. It is not quite honest. Multiplicities will differ, but you see that we always have this one, and this one, and this one. If you want, we have another copy of SL2. We have this one. With respect to this, we will have another decomposition. And we have also this one. We'll get the third one decomposition. Окей. Так, картиночка понятна? Хорошо. So, what is very important? We did not say what can be weights taken from. What are the weights which can appear? So, I state the following. So, possible weights. So if we take lambda alpha, which is in fact lambda alpha to lambda alpha should be integer. Do you remember this was the condition in the root systems? So if we take some lambda, and this is very similar to an alpha chain. Да.
Сейчас weights в смысле формы?
Не совсем. Ну как же? Сейчас, у вас была же Жорданова нормальная форма?
Когда-то было.
Да. Вот, ну тут почти то же самое. Вот вы взяли диагонализуемую матрицу. Вот когда была размерность 1, вот здесь вот, у вас была диагонализуемая матрица, у нее есть собственное значение. Как бы в размерности 2 у вас диагонализуемая матрица, помните, мы в тот раз коммутировали. У нас вылезли собственные значения какие-то там типа x1 минус x2, x1 плюс x2. Вот в базисе двойственного пространства это какие-то векторы. То есть если бы у нас здесь h было трехмерное, мы бы в трехмерном пространстве рисовали эти векторы, которые собственное значение. Это такой, да, непростой перескок, понять, что собственные значения живут в пространстве, что это не чиселки, а векторы теперь. Ну вот, как бы веса — это возможное собственное значение. Вот. Yes, so weights are possible values of lambda. I want to explain why weights are the vectors which can be described as follows. Some integer condition. So why? Because if we take lambda, v lambda from the corresponding eigenspace, and we take the alpha series, so it lasts on this direction and on that direction, and its length is in fact this stuff. You have checked this at the seminar. The length of our alpha series is this number. And so this series should be finite because our representation is finite dimensional. At some step it stops, so that the next one will vanish. And we will obtain that the eigenvalue of h, of this h, will be minus m, where m plus 1 is the length of alpha series, since we know all the representations of SL2. So the representation of SL2, it should be 3, 1, minus 1, minus 1, and minus 3. The eigenvalues of this element h lambda. For one element h lambda, h alpha, eigenvalues are numbers. For the whole subalgebra, this will be a vector. So the length of alpha series is 3, so it will be described as follows. So these scalar products should be integer. Otherwise, we will never stop. It will be an infinite dimensional representation of SL2. This is not a proof, this is an explanation. Okay. Примерно понятно? Что?
Метод доказывает.
Нет, я вроде, ну как бы,
На принципе.
давайте я вот пример какой-нибудь нарисую. Лучше. Давайте мы поймем, почему мы поверим в действие. Let us explain why the whale group acts on this set. So we know that the whale group is generated by simple reflections. I need one more page. So W acts on the set of weights of representation. So the same set, it is generated by simple reflections, and for each simple reflection there is an SL2 triple. No, this is not exactly the same set. One moment. This is our new set. So SL3, this is SL3, A2. So for sigma alpha, how was it defined? So lambda should go to lambda minus to lambda alpha, 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 alpha. So this one, if this is alpha, this is minus alpha. We just know that for each alpha, we find an alpha series. We have if so to this equals m, then from this vector we can go here and vice versa. So m switches with minus m minus 2 switches with minus m plus 2, and so on. So we just subtract some copies of alpha. And the next very possible value is we subtract m. Lambda goes to lambda minus m alpha. So for each alpha, this simple reflection sigma alpha, it reverses all the alpha chains. We split our set of weights into alpha chains, and it reverses the order. So in fact, we have 3 sigma alphas here. This one, then this one, and the third one, and this one, and all the generators of the wave group act in our set. And the extremal elements, they are also, so where is our center? It is not always in our set. This is our center, the center of this triangle. So this reflection maps it here. Which reflection? This one maps it here. This reflection again maps it here. So we obtain all the vertices of our polygon using the wave group. В смысле, центр я просто отметила, что центр был.
Вот такая его.
Okay, so let me erase the center if it causes problem. Do you remember that we said that we have 0 only when n is even for the SL2 representations? Let me draw you the example for SL2. Picture from what is the condition that 2 lambda alpha is integer? Suppose that our vector alpha is 1. Okay? It means that 2 lambda is integer. Okay? So this is our line. If we take this is our root system, and this is another picture for all possible lambdas. For example, we can take lambda equals to 1/2. Then the set of weights is invariant under the action of wave group. We have 1/2 and minus 1/2. So this is a representation of dimension 2. The only alpha chain is this one. We have 2 points. And we don't have 0 in this set. However, if we start with 1, then we will have 1, 0, and minus 1. This is the set of weights of representation of dimension 3. If we take the representation of dimension 4, it will start with 3 halves, and it will end with minus 3 halves. Indeed, here n is odd, and it doesn't contain 0. So at that picture, we have the similar situation. For example, if we start with this vertex, then we will have a 0 in our set of weights of the representation. This is our alpha chain, another alpha chain, another alpha chain, another alpha chain, and 0 is in our set. But for this choice of the lambdas, 0 is not in our set of weights. I think we will make the example in the seminar. So the theorem is that for any Lie algebra G, for any G semi-simple Lie algebra, so each irreducible representation is given by its highest weight lambda, and the set of weights is, as it is written here, is first of all we take W alpha, where W is the Weyl group, and then we intersect it with alpha plus lambda plus Z root system. So first of all we apply the Weyl group to obtain the polygon. And then we know that what are the alpha chains? We subtract some integer number of root alpha. So this is description of the set of weights of an irreducible representation. I have written highest weight here. What is the highest weight? Do you remember we've had simple roots? Simple roots at this picture can be chosen, for example, in this way. If we choose these simple roots, we've had the Weyl chamber. The Weyl chambers, we split all the space into Weyl chambers. And one of them was the distinguished one. At this picture, what is the Weyl chamber? This is orthogonal to this one, and this is orthogonal. One moment. Yes, this to that one. It passes through the middle of this segment. This is the distinguished Weyl chamber. So all the weights which belong to this Weyl chamber, they are called dominant. For this case, this is dominant. So in some sense, this is highest, and we can take it and take W lambda for it. So the highest weight is the weight which belongs to the principal weight chamber. So it is not negative with all the simple roots. So I think I'll stop here, but if you have questions, we will discuss them 10 more minutes. Вопросы? Ну, есть какое-то понимание?
Очень плавно.
Ну, нет, кажется, это материал на 6 лекций. Я немножко решила. So, I discuss it here because usually in the course of the algebras, this combinatorial description is omitted. Even in Humphreys, it is described by words. So if you really want to work with this stuff, I think it is a very convenient formula. And we can explain it why is, for example, this set invariant under the wave group.
Что такое дублевая лямбда?
Группа Вилли есть у нас?
А?
W lambda. So W lambda is the orbit of lambda. We have different kinds of points. For example, here you see, for example, for this point, it is in the interior of the wave chamber. So its orbit contains 6 elements. If you take any point at the boundary of this wave chamber, so its orbit will contain 3 points. I need one more color. So for this point, it is on the boundary, so its orbit contains 3 points. For example, if I take the origin, its orbit contains only 1 point.
Origin это что?
Origin, начало координат. Как вот здесь по магазину начало координат. Вот, одновременно повторение. So, for example, for this one, we will also have 3 elements in the orbit. You see? Some reflections act trivially on those points. So we take this polygon. Maybe we should add convex hull for completeness. And then this is the lattice generated by all the roots. In this case, it is the lattice of all the integers. So in this case, z5 equals z. And we shifted so that it starts from lambda. If we shift it to an integer, it will remain integers. And if we shift it to a half integer, it will be all the half integers. Еще вопросы? Я не могла пройти на представление.
Хорошо.
Давайте разом сeminar. So then I give you the seminar problem, and if I forgot to say something, you ask me questions about this seminar problem and about the notions used in it. Да. Давай, сейчас. Я все вошла условия скажу. Какие условия? Не на том, что не знаю. А? Сегодня такой день, когда можно сдать, да. Но семена для тех, кто уже все сдал, и ему нечего делать.